Hello everyone, this is Dr. Ranjith Kumar Gatla, working as an associate professor in the Department of Electrical and Electronic Engineering, Institute of Aeronautical Engineering. In today's class, we are going to discuss about the single phase bridge rectifiers. In this class, we are going to discuss the single phase bridge rectifier, which means the full bridge rectifier as well as the half bridge rectifier, and with R and RL load. These are the things that we are going to discuss in this today's class. And as we discussed in the previous class, that is the midpoint converters. In that also, what is that R and RL load that we have discussed? Okay. So today we are going to discuss another type of converter, that is the bridge converter. In that, the first one is a single phase full bridge converter. As we discussed earlier, the single phase full bridge converter, what is mean like the different types of converters. One is based on the construction. Okay, like as we can see in the same full bridge converter, there are two different types of full bridge the full converters. Okay, there are two different types of full converters. One is the midpoint full converter, another one is the bridge type full converter. And in the bridge type full converter, as we have discussed, as we have seen in the last class, another type is the midpoint. The midpoint that we have seen in the previous class. Okay, by using midpoint transformer, we are giving the AC supply to the converter, which is the rectifier. So here, this is another type of what is that full converter, that is the bridge type full converter. So in this, first we are going to discuss about the full bridge converter with R load. So here again, the function here, this is also a rectifier, so which means it can convert AC to DC. Okay, so then when coming to the the construction point of view, the full bridge converter, unlike the bridge type converter, unlike the midpoint converter, here the full bridge converter having four thyristors, namely T1, T2, T3 and T4. And there are two legs, and each leg having two thyristors. And these two thyristors are connected in series, and the two legs are connected in parallel with each other, and the load is connected to the parallel combination of these two legs. And usually here, before going to discuss the operation of this full bridge converter, let me tell you some important points about this full bridge converter. Here, as we can see, each leg having the two thyristors T1 and T4. Okay, so there are some conditions that we must follow before going to discuss about the operation of this full bridge converter. The first point is the two thyristors in the same leg should not turn on at the same time. The first condition is the two thyristors in the same leg should not turn on at the same time. Okay, or should not be should not be in the turn on position at the same time, which means when the T1 is turned on, then T4 must be turned off, turn off position. And when the T4 is turn on position, then T1 must be in the turn off position. Similarly, in the second leg, when the T3 is turned off, then T2 must be in the turn off position. And when the T2 is turned on, then the T3 must be in the turn off position. Otherwise, suppose if the two thyristors in the same leg will turn on at the same time, okay, or during the same period, if the T1 and T4 are turned on, then the short circuit will get across the load, so that the load will get damaged. Suppose if you consider RLE load, which is nothing but a DC motor, then the DC motor will damage. To avoid that, we must turn on simultaneously T1 and T4, which means when T1 is turned on, then which means in each leg only one thyristor should be turned on at a time. Okay, and then when coming to the operation here, as we know, the input, let me consider here it is Vs, and then the input is sine wave because we are giving the AC supply, right? Then here this is the pi, 2 pi, 3 pi and 4 pi. Let me consider here it is omega t. Then next I am going to draw the gate signals. I mean during the positive cycle, because as we know this is the positive cycle and this is the negative cycle of the input supply. And during the positive cycle, what are the thyristors going to turn? I mean, we should turn on, and during the negative cycle, what are the thyristors going to turn on? That we will discuss. Okay. So during the positive cycle, okay, here this is the positive and this is the negative. Let me consider here Vs. Okay. During the positive cycle, the forward biased voltage applied across thyristor T1 and T2. The forward biased voltage applied across the thyristor T1 and T2. Then the load current will flow from the positive, I mean, which means Vs positive to thyristor T1 to through the load to thyristor T2 to and Vs the negative, which means here from here to T1, from T1 to R load and R load to T2, T2 to this negative supply. This is the path of the load current which will flow from T1 to T2. Then by simply applying the forward biased voltage across the T1, T2 will not turn on. Okay, we must give a gate signal for the T1 and T2. Let me consider here, let me consider here I, G1 and G2. So I am giving the gate signal for the T1 and T2 at an angle of alpha. At an angle of alpha, then the thyristor T1, T2 will get turned on. Okay, then the load current will flow, which means, let me consider here, this is the output voltage. So at this particular point, it is turned on. So which means from here, like this, you will get the output voltage. Then up to pi degrees, after pi, immediately the reverse biased voltage applied across the T1 and T2. Then the forward biased voltage applied across the T3 and T4. So when the reverse biased voltage applied across the T1 and T2, then the T1 and T2 will get turned off at pi. Then again after pi plus alpha, because similar like in the positive cycle, okay, during the negative cycle also, of course there is a forward biased voltage applied across the T3 and T4, but still T3, T4 will not get turned on until we must give the gate signal. Then here, let me consider here, these are the IG3 and G4, the gate signal for the thyristor 3 and thyristor 4. Then at pi plus alpha, I am giving the gate signal for the thyristor 3 and thyristor 4. Then the thyristor 3 and thyristor 4 will get turned on at this point. Then the thyristor 3 will get turned on up to 2 pi. Because again after 2 pi, what is that? The voltage will be get into the positive cycle. So that which means again the reverse biased applied across the thyristor T3 and T4. So that the thyristor T3 and T4 will get turned off. Already the thyristor T1 and T2 are in the off state. Okay. Then again you have to give the gate signal for the thyristor T1 and T2 after 2 pi plus alpha. After 2 pi plus alpha. Then again, so which means here T1 and T2 will conduct, and here T3 and T4 will conduct. And again after 2 pi plus alpha, we are giving the gate signal to the thyristor T1 and T2 because of the positive cycle, the forward biased voltage applied across the T1 and T2. So that here again the T1 and T2 will get turned on, so that again the load current will flow in the same direction. When T3 and T4 are turned on, because of the the negative voltage, because here it is minus and here it is plus, so then the load current will flow from here to T3 to load to T4 to the point A. Okay, so this is the direction of the load current. So which means in the both the direction, the load voltage and the load current are in the positive direction only, because as we have seen, when the T1 and T2 are turned on, what is the direction of the load voltage and current? Okay, which is same when the thyristor T3 and T4 are also turned on. So which means the current, the voltage is positive. Okay, in the two cases. So which means in the second case, Vs negative 2, okay, T3 to R to T4 to Vs positive. This is the direction of the load current flow. So similarly, what is that? The cycle is repeating. Okay, and when coming to the load current, as you know, because this is the R load, so in this case, the load current will also, the waveform of the load current will also same like as the load voltage. So which means here you will get more or less the load current is also same like the load voltage. And again here T1, T2 will turn on something like this. The same thing here I have represented, that you can see. One second, let me just erase this one so that it will be clear, visible. Yeah, here you can see at alpha we are giving the gate signal Ig1 and Ig2, which means the gate signal for the thyristor T1 and T2, so that the thyristor T1, T2 will get turned on during the positive off cycle. Okay, then we will get the load voltage and load current, which will follows the input, the source voltage. Okay, and similarly at pi plus alpha, during the negative cycle, the reverse biased voltage applied across T1 and T2. Because of that, the T1, T2 will get turned off. Then the forward biased voltage applied across the T3 and T4. Then we are giving the gate signal for the thyristor 3 and 4 after pi plus alpha. So here the thyristor will get turned on. Here the thyristor will get turned on at this particular Ig, pi plus alpha. Okay, then you are getting here, this is where this is the output current, and similarly the output voltage. And when coming to the voltage across the thyristor, because here as we can see the voltage across the VT1 and VT2 is same, because the both thyristors are turning on for the same time period. Okay, so which is the thyristor T1 and T2 is turning on from how long it is turned on from pi to pi plus alpha. So that's why during this time the voltage across the thyristors are 0. Okay, and here during this time it was turned off, so that's why here we are getting the voltage across these two thyristors is the same like the supply voltage, and during this time also it is turned off. Okay, so but here the reverse biased voltage applied across these two, that's why here we are getting the reverse voltage across the thyristor VT1 and VT2. So similarly VT3 and VT4. So this is the operation of the single phase full bridge converter with R load. Then similarly we will discuss about RL load. This is the same single phase full bridge converter with RL load. As we have already discussed the full bridge, the midpoint converter with RL load. So here more or less the output waveforms are same, but the operation is little bit different, because there it was only two thyristors that midpoint converter having, but here the full bridge converter having four thyristors. Okay, so here again the operation is same like when the positive cycle is applied, during the positive cycle, the thyristor T1 and T2 will get turned on. Then the load voltage or the load current will go through from T1 to inductor to R2, T2 to this negative terminal. And during this, when during the T1 and T2 are turned on, the inductor will store some energy by making the polarities as plus and minus like this. Then again during the negative cycle, the reverse biased voltage applied across the T1 and T2. But anyway here, during when it reaches to the pi, okay, when it reaches to the pi, then at that particular moment, the thyristor, I mean these inductor will discharge during pi to pi plus alpha with by changing the polarities minus and plus, which means some reverse biased voltage will flow through T1 and T2, so that here you will get from pi to pi plus alpha the reverse biased voltage until the thyristor T3 and T4 are turned on. When the thyristor T3 and T4 are turned on, then immediately the T1, T2 will get turned off, because as we know, the conditions to turn off the thyristor, the commutation techniques that we have discussed, okay, so that is we must apply the reverse biased voltage to turn off the thyristor, which means we must supply some amount of the reverse biased voltage to turn off the thyristor, right? So which means it will allow some amount of the reverse biased voltage until the anode current reaches the below the holding current. Once the anode current reaches the below holding current, then the thyristor will get turned off. So that's why here we are getting some amount of the voltage, right? So then similarly, during the negative negative off cycle, the thyristor T3 and T4 will turn on. Then at the same time, the thyristor T1, T2 will get turned off. Then the load voltage will get like this. Again, the positive load voltage we will get. Then during this T3 and T4 are turned on, again the inductor will get charged with these polarities plus and minus. Then when it is reaches to 2 pi, okay, then again the load, I mean the inductor will discharge by making the polarity, by changing its polarities like minus and plus. So like this, here you are getting the negative portion for a particular duration. Okay, for the duration is around alpha. So that's why here the full bridge converter is also called as, I mean, which means not only full bridge, the full converter, I mean especially the full bridge converter is also known as two quadrant converter. Okay, so why? Because here let me consider here, just I have considered these waveforms are for alpha is equal to 60 degrees. Alpha is equal to 60 degrees. So let me take for the same operation for alpha is equal to I mean greater than 90 degrees. Okay, so here this is the waveform for alpha is equal to 135. So for alpha is equal to 135, as you can see here, the negative portion of the output voltage waveform is higher than the positive portion. This is because this is the output voltage waveform. So then the average voltage is negative. The average voltage is negative, because as we can see here, the average load voltage equation, that is 2 Em by cos alpha, when alpha is equal to 0, so EDC, which you will get 2 Em by pi, which is maximum. Okay, and this is when alpha is equal to 0, this EDC is the maximum. And when alpha is equal to 90 degrees, okay, then this EDC will become 0, because cos 90 is 0. and when alpha is greater than 90 degrees, then EDC, the average value, will be negative. So that's why here I mean, here you can see, let me consider, this is I naught and this is the V naught, that is the output voltage and the output current. So for alpha greater than 0 and less than 90 degrees, okay, then both voltage and current are positive, because anyway the current is always positive irrespective of the alpha value, because let me just consider same like in the midpoint converter. Here also you can just consider the inductor value is very high, so that we will get the constant load current which is always positive. And when here it is minus V naught, and here it is minus I naught. And here when the alpha is greater than 90, which here alpha is the firing angle, greater than 90 and less than 180 degrees, then you will get the negative. The voltage is negative. So that's why we can operate the single phase full bridge converter in the two quadrants. Okay, that's why this is also called as a two quadrant converter. Okay, yes. Then how to derive the output, what is that, average load voltage and RMS load voltage and load current. Okay, so again the same basic equations that I am writing here. For the average V average, which is equal to 1 by T into integral 0 to T Vm sin omega T into d omega T. Similarly, Vrms equal to 1 by T into integral 0 to T Vm sin omega T whole square into d omega T whole to the power of 1 by 2. So here the only thing that we need to concentrate on, what is the total time period of a particular waveform and what is the conduction period of the waveform, that we need to identify from the output voltage waveform. Then when coming to the first V average, 1 by, here the time period is again we can consider as a pi, because from 0 to pi the waveform, the shape of the waveform is similar to the shape of the waveform from pi to 2 pi and 2 pi to 3 pi, which means for every pi degrees the shape of the waveform is same and repeating. So that's why here 1 by pi, and the conduction here it is starting from alpha. Okay, so alpha to how long it is conducting, pi plus alpha. Okay, not only here, okay, still here it is conducting only, right? So that's why here it is pi plus alpha into Vm sin omega T into d omega T. Then the integral of sin omega T is minus cos omega T. Then you can just apply the integral limits. Then you will get here, as I have mentioned here, that you can see here. See, now 1 by pi into integral alpha to pi plus alpha em sin omega T into d omega T. So here then this sin omega T, the integral of sin omega T is the minus cos omega T, and the limits are pi plus alpha to alpha. Then if you substitute these limits, then it will become Em by pi into cos alpha minus cos pi plus alpha. Then if you simplify this, because again here cos alpha is there, again here cos alpha is there. Okay, so and the cos pi, which is 0. So then here Em by cos alpha plus cos alpha, here it is the cos pi plus alpha is minus cos alpha, so minus cos alpha of minus cos alpha minus plus cos alpha, then Em by pi into 2 cos alpha. So then the EDC, which is equal to Em by pi into cos alpha. Similarly, if you want to id, then you just what is that edc by r, then you will get id, that is the average value of the dc current. Similarly, rms also you can find. So in case of rms, the equation will become erms, which is equal to 1 by pi into integral alpha to pi plus alpha em sin omega t whole square into d omega t whole to the power of 1 by 2. So this is by simplifying this, we can find the ERMS value. Similarly, like IRMS is equal to IRMS is equal to ERMS by R. Then next, this is how just now I have explained when it is what is that because of the negative voltage, okay, the full bridge converter can be operate in the two modes. One is the rectifier mode, another one is the inverting mode. Because as we know here, as we know when it is a rectifier, which means here AC to DC, right? AC to DC. Okay, this is the rectifier. And when coming to the inverter, the opposite, this is DC to AC, right? So when what is that alpha to pi, okay, then the inverter, the converter will act as a rectifier, which means in between 0 greater than alpha less than 90 degrees. During this period, the both voltage and current are positive. So which means here this is the supply or source, and this is the load. So the source will supply to the load, and when alpha is greater than 90 and less than 180 degrees, then here the voltage is negative, which means the total power will get negative. Okay, so which means here in this case it is the power is flowing from in this direction, but in this case, okay, again let me draw the same way. Like here also, let me consider it is a rectifier, AC and DC. This is source and this is load. But in this case, power is negative, which means this is opposite direction to the positive power. So which means here from here it is from in this way. This is the direction of the power. So which means from DC to AC. So what is mean by DC to AC? A converter which is converting from DC to AC, which is nothing but an inverter. So that's why the full bridge converter can be operate in the rectifier mode as well as the inverting mode. So how we again, by changing the alpha value, that is the firing angle value. So if you consider the alpha value in between 0 and 90, then you can operate this one as in a rectifier mode, which means the source will supply to the load, and when alpha is in between 90 and 180, then the load will supply to the source. This is usually we use in the regenerative braking system. So while applying the braking, we are regenerating the power. Okay, and that power we can utilize by connecting a load to the source, or extra load to the source, or a battery, so that we can collect the power which is supplying by the load. So this is all about the single phase full bridge converter with R and RL load. Then the next topic is the single phase half controlled bridge rectifier. So why it is full controlled and half controlled means, here in case of full controlled, all the full switches are controllable because thyristors, and in the half controlled, half of the switches are controllable and half of the switches are uncontrollable. That's why here you can see T1, I mean the upper switches are controllable and lower switches which are D1 and D2 are the uncontrolled diodes. When coming to the operation is same. I mean the single phase full bridge rectifier with R load and single phase half bridge rectifier with R load, the operation and waveforms are more or less same. Okay, as you can see here, during the when during the positive cycle, T1 and D1 will get conduct. Okay, so T1 and D1 will get conduct. Then when you are giving the firing angle alpha to the gate signal to the thyristor T1, then the thyristor T1 will get turn on. Then already forward bias is applied, so that's why D1 will also starts conducting. Then this is the load voltage. Then after pi, the reverse biased voltage across T1 and D1. So because of the reverse biased voltage across T1 and D1, so of course anyway the D1, the diode will not allow the reverse biased voltage, but the T1, because of the reverse biased applied, then T1 will turn it off immediately. Then the forward biased applied across T2 and D2, but of course D2 will allow to flow, but here T2 is still in the turn off position because we didn't give the gate signal to the thyristor T2. Then by giving the gate signal to the thyristor T2 will turn on. Then again here the load voltage you will get. So here T1 and D1 are turned on. Here T2 and D2 will get turned on. Okay, so this is how the process of the single phase half controlled bridge rectifier. Okay, similarly in the RL load also, as you can see, that we will discuss in the next class. Okay, in the RL load, how it is again here. In the single phase half control bridge rectifier, there are two different types of half control rectifiers are there, and symmetrical and asymmetrical configuration. Okay, that we will discuss in the next class. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.